So we're going to revisit now some previously discussed facts about determinants from multivariable calculus. Everyone in this class should have had a course in multivariable calculus. In our multivariable calculus course here at Duke, here is one of the standard facts that gets presented. If you have two vectors in R2, and if you do two things with those two vectors, first take those two vectors and make them the columns of a matrix. Second, take the same two vectors, represent them geometrically, right, and then make the corresponding parallelogram. This old fact from Math212 says that this matrix and this parallelogram have a strong connection by way of determinant. And here's the connection. The absolute value of that determinant of that matrix is equal to the area of that parallelogram. That's really a pretty surprising fact when you first see it. I'll just remind you that the determinant, the formula for determinant here, is a little combinatorial, three-function arithmetic: multiply, add, subtract. Right? Really easy little operations involved in the formula, and yet what it computes is the area of this parallelogram. And golly, if you think about what would go into computing this area, computing just that length would involve a square root. Likewise, computing that length would involve a square root, and somehow or another we're going to have to figure out what that angle is, and trigonometry is going to get involved. It seems like the operations that would go into computing this area would be uglier. Amazingly, the determinant, the absolute value of the determinant, is equal to the area. Now, more is true. That's just the absolute value of the determinant. The sign of the determinant tells you about the order that the vectors, the original pair of vectors, was listed in. Now, the order is important. You'll notice that I had A listed first, so A goes in and becomes the first column. B is listed second. B then becomes the second column. Likewise, A being first and B being second, indicates which one I'm going from and which one I'm going to in thinking about whether the order is counterclockwise, as in this case, or if they were written in a different way, clockwise perhaps. Okay, so the order matters both to the parallelogram and to the matrix. Okay, so keep that in mind. All right, and so what does the sign tell us? Well, the wonderful result is that if the determinant is positive, then the vectors were listed in counterclockwise order, as per this picture. Counterclockwise, from the first to the second, counterclockwise. On the other hand, if the determinant were negative, that would mean the vectors were in clockwise order. That's the other way that this picture could have been drawn. And furthermore, if the determinant is 0, then those vectors are in neither order. Now, that can come in a variety of different ways. The vectors might be, for example, parallel. That's neither clockwise nor counterclockwise. Or the vectors might be, one of them might be the 0 vector. Well, it doesn't make any sense to talk about clockwise or counterclockwise in cases like that. Okay. All right, so this is one of the facts mentioned about determinant in Math212. I hope this looks familiar to everyone. Here is a analogous fact in 3 dimensions. And if your vectors first, second, third, this is now 3 vectors. You'll notice in R3. Right, and again, make the two things. On the one hand, make those the columns of a matrix. On the other hand, make them the edges of a parallelepiped. Right? And the determinant of this matrix tells you much information about this parallelepiped. So exactly an analogy, the absolute value of the determinant tells you the volume of that parallelepiped. And furthermore, the sign of that determinant, whether it's plus or minus or 0, tells you about the order that these vectors were listed in. And keep in mind that order, there's 3 different possibilities. When you have 3 vectors listed in an order, they can either be right-hand order or left-hand order, or again, anomalous cases could be neither order. Okay. Right. So interesting that this fact about determinants in 2 dimensions, this fact about determinants in 3 dimensions look so similar to each other. Okay, now this is all Math 212 review. Our goal here is to take a more sophisticated point of view on these facts. And the way we're going to do that is we're going to take a different point of view on the matrix. Rather than thinking of the matrix as a static thing, I want to reinterpret the matrix as a function. Something that's doing something. It ends up making a big difference having this capability. So here's the way we're going to do this. We're going to think of a matrix as a function by that formula. A matrix can be thought of as a function by, well, multiply it by input vectors to get output vectors. Right. Notice that if you take an n-dimensional input vector, multiply it by A, don't forget A is an n by n matrix, right? Then the output is an n by n matrix, this formula being the output. The output is an n-dimensional vector per this formula. Okay. So now, thought of no longer as just a matrix that's just sitting there, thought of as a function, we're going to be able to reinterpret the facts on the previous page about determinant. Now, in order to do so, we need to make a few observations about this function. Here's the first one. That is, the columns of the matrix are the images of the standard basis vectors. This is just a calculation. It's an easy calculation to write down. Images of the standard basis vectors. This language here, images of the standard basis vectors, just says, well, plug in the standard basis vectors E1 through En, plug those into T. So T of E whatever is what we're talking about here. The assertion is that these are the columns of the matrix. Well, let's compute and see if these are indeed, as expected, the columns of the matrix. Well, here's a formula for how we compute this function T. That's just the definition of this T function. Notice we need to multiply a matrix times a column vector. Right. Furthermore, that column vector is a standard basis vector. Standard basis vector is just made up of mostly zeros with a 1. Now this is EI specifically, and that means we have a 1 in the ith position. And that's where that is. Okay. So how do I multiply this out? Well, again, you can take different points of view on how to multiply matrices. The point of view I want to take here is that these numbers here are the coefficients and a linear combination of the columns of A. Again, there's many different points of view you can take on matrix multiplication. This is the one that's convenient here. And this is, so we have here a linear combination of the columns of A, but it's a special linear combination where almost all of the coefficients are 0. Only a single coefficient is not 0, so only a single column, in particular the ith column, remains. All the other columns are multiplied by zeros and disappear. Okay. So we have a wonderful result, and that is the columns of the matrix are the images of the standard basis vectors. It ends up being really important. We're going to make use of it here, but we're going to be making use of this fact many times throughout this course, and we'll revisit this again in Chapter 5. But do remember this little phrase here, that the columns of a matrix are the images of the standard basis vectors. Okay. All right. So with that in mind, let's reinterpret our statement about this parallelogram. Where does this parallelogram come from? Well, previously we had decided that the parallelogram was, well, what you get when you take the matrix A, the vector A and the vector B, and you make this parallelogram. Well, what were A and B concerning the matrix? Concerning the matrix, A and B were the columns. Well, the columns are the images of the standard basis vectors. So instead of just thinking of these as being just the vectors A and B, let's think of these as being the images by way of this new function that we're talking about, t, the images of these standard basis vectors here. All right. So E1 and E2, plug them into the t transformation, and out come our A and our B. Okay. Now, an exercise that I'm going to leave to students to work out is that not only are these vectors the images of those vectors, but in fact, this edge here is the image of that edge, and this edge is the image of that edge. This can be achieved by sort of just a direct calculation. Parameterize these edges. This is a Math212 thing. Parameterize those curves, they're straight lines, of course, and then take those formulas for these parameterizations and apply t to them. In other words, multiply by the matrix A, and you can confirm that you'll get these edges of this parallelogram. Okay. All right, so what we have then is that P, this parallelogram, don't think of this as something that's made up in static, just coming from the vectors A and B. Think of it as being the image of the unit square. Right, that we started with this thing, S, this square, and that its image now is P. Okay. Likewise, for the three-dimensional case, these vectors that we use to define our parallelogram in the first place, well, those being as they are the columns of our matrix, are the images of our standard basis vectors. That makes them the images of these vectors, and likewise, the entire parallelepiped is the image of this unit cube. Okay. All right, so now let's keep this in mind and try to make new sense out of our old formula here. Here's our old formula from Math212, is that the absolute value of the determinant of the matrix is the area of the parallelogram. Okay, sure. But don't forget, this parallelogram came from this unit square, and the unit square has area equal to 1. So if I were to, for example, divide by the area of S, I'm dividing by 1. I didn't really do anything there. So what we have then is that our old formula, reconceived, can be thought of as a area stretching factor. Right? The absolute value of the determinant you see here is the proportion of the output area of the parallelogram and the input area of S. It's how much this function here has stretched out areas from the input to the output. The proportion, that area divided by that area. Okay. So instead of thinking it as an area, which is a static thing, we can think of it as a factor, an active, a process sort of a thing, a stretching factor. How much did areas get stretched out by? Right. So it's not a new result, but it's a new point of view on our old result. I'll point out, for those of you who might recall how to do change of variables in multivariable calculus, this factor is related to the change of variables formula for integrals. In fact, the matrix is the Jacobian matrix for this function t. And this is a nice exercise, and I think everyone should give this a shot. Take this function, write down its Jacobian matrix, and confirm that that Jacobian matrix is exactly A. Okay. All right. Now, what about this old fact about order? You know, so we've seen a new interpretation of the absolute value of the determinant, no longer as an area, but now as an area stretching factor. What about the sign of the determinant? Well, our old point of view on that was that it gave us information about the order, what the order is. Is it clockwise? Is it counterclockwise? Our new point of view, again, comes from the same observation, thinking about how not just how this pair of vectors is, but how it relates to the original. Notice that E1, E2 is always counterclockwise. Right? That's what it is. E1 is there, E2 is there. That's a counterclockwise order. E1 going first, E2 being second. So now let's consider the case as I have it drawn here anyway. In this drawn case, T of E1 and T of E2, what would I make of the assertion that this is a counterclockwise order? Well, the observation I would make is that this counterclockwise pair of vectors turned into another counterclockwise pair of vectors, and so the handedness was preserved. On the other hand, let's imagine a different scenario. Where instead of the vectors being in that order, I'll just scratch these off to get them out of the way. Suppose that that was A and that was B. In other words, let's consider the case where they're in counterclockwise order. Well, that would mean that this function t is taking a counterclockwise order and turning it into a clockwise order. And let's just digest for a moment. What would this mean? What does it look like if a counterclockwise order by way of this function turns into clockwise? Well, I'm going to appeal to your geometric intuition that it would have to flip it over. This function t, which we'll later come to know as something called a linear transformation, flips the vectors over. That's the only way that you can turn a counterclockwise into a clockwise. Okay. So again, we're interpreting the determinant now not as a statement about the parallelogram, but as a statement about the function, this function t. So, summarizing, the absolute value of the determinant tells us how much does this function t stretch things out area-wise. The sign of the determinant tells us whether this function flips things upside down or leaves them right side up. Okay. All right, now a very similar argument can be made for the three-dimensional case. It's a little bit geometrically more convenient to talk about in the 2x2 case, but a very, very similar argument for 3x3. Let's go back up to here's our picture, 3x3 case. We already know that the determinant of the matrix tells us, well, the absolute value of the determinant of the matrix tells us this volume, right? But of course this volume is 1, and therefore the ratio of that volume divided by that volume is the same thing as the original volume, and so our new interpretation of this old Math 212 fact that the absolute value of determinant is the volume. We can reinterpret it as saying that it's a factor by which T stretches volumes. And again, you can check for yourself that the matrix A is the Jacobian determinant, the Jacobian matrix that you would use in the change of variables formula to compute the area, the volume, that is, of that parallelepiped. Okay. And now here's the one that's a little bit geometrically confusing. To think about order, we know that this trio, let me do this color, so E1, E2, E3, that is always a right-hand order. They are. That's just what they are. They are, E1, E2, E3 in that order is a right-hand order. It's always the same vectors, always right-hand order. The sign of the determinant is going to tell us whether this listing is either right-hand order or left-hand order. So instead of thinking about that as whether it is or is not right-hand order, let's think about it as, is it the same as it started, or is it different? And geometrically, the interpretation that we would take, what does that tell us about this function? Is that if these are in the opposite order, if these are, let's say, left-hand order, let's think, geometrically, what would this function have to do to take vectors that are in a right-hand order and somehow get them to be in left-hand order? What can you do to a right hand to make it look like a left hand? And that's a reflection, right? If this sign is negative, that would mean that the vectors are in left-hand order, which means that they are a reflection of sorts of the standard basis vectors, combined with other manipulations, but there would have to be a reflection in there somewhere. So these are our new interpretations of these old Math 212 facts. The absolute value of the determinant is an area stretching factor. The sign of the determinant is an indicator of whether there's a flip. For the 3x3 case, the absolute value of the determinant, volume stretching factor, and the sign is an indicator of whether or not the function reflects.